This course was meant to be a story in sort of 3 parts. And it started with a discussion of metric spaces, and then topological spaces, and quadratic spaces. And these were all spaces of a certain kind, which I described as somehow like things, whatever that means. So circles or ellipses or spheres, tori. And within that class of topological spaces, we came to understand that a particularly well-behaved kind of space was compact Hausdorff spaces. Now, these are good spaces. And we saw various examples of those kinds of spaces. And then in the second part of the course, we were concerned primarily with function spaces. And I started off that part by discussing an example, which is configurations of a string. So that was this space. And we discussed how it was reasonable to expect that there was a sense in which 2 configurations or functions could be close to one another, and in fact we made sense of that. And this is a very well-behaved kind of function space. I mean, it's not compact Hausdorff, so this is a different sort of category of spaces, but this is nonetheless a well-behaved topological space with a compact open topology. So in this part of the course was sort of conceptually organized around the adjunction property. That's what we used to discover, in some sense, the compact open topology, and what we use in practice to prove many things about function spaces, as I hope has become clear. And in a sense, what the adjunction property tells us is that the following map, this is what it says in its content, is that this map is continuous, the evaluation map, as long as X is locally compact Hausdorff. Right, so if you like, this was the central or fundamental fact about function spaces was that is continuous. And that is what tells us that we're talking about functions, right? The characteristic property of a function, is that you can evaluate it somewhere and get an output. That's what a function is, right? So the fact that this is continuous is connected to the fact that the points in these spaces are functions, and we're talking about spaces of functions. Okay. So one of the key insights we got from that story was Stone-Weierstrass. And what Stone-Weierstrass said is that if we start with one of these well-behaved spaces, and well, we also assume it's embedded in Rn, all right, so X is compact, it's automatically Hausdorff if it's embedded in Rn. Then we found out that polynomial functions on X are dense in this space. In particular, that applies to this example, right? So that tells us something very strong, apparently very strong about the compact open topology and function spaces. And so that was sort of the second third of the course. And then the part we're in now has been building up to a discussion of these kinds of spaces. Right, so as we know, these are Hilbert spaces. So we're going to spend most of today's lecture discussing the example of X equals S1. But actually everything we're going to say, I'm talking about the case of the circle because it's concrete, but everything we're going to say has an analog for any X compact and embedded in Rn. Right? So we will have something very conclusive to say about L2 spaces by the end of the lecture. But it should remain a little mysterious exactly how you're supposed to think about these kinds of spaces. I mean, we've discussed by now a few ways of thinking about vectors in this guy, right? They're either Cauchy sequences of continuous functions. That's how we constructed them. Technically, that's fine. But that's maybe a little distant from our intuition, right? Maybe a little is understating it. Okay, so vectors in there are Cauchy sequences. What we saw in the tutorial today, how to also think about vectors in here as arising from integrable functions. So one is tempted to think that, well, there's a line here for a reason. Okay, so this thing arose as a completion of one of those spaces, right? So in some sense it's quite close conceptually to a function space. The vectors in here come from integrable functions. So maybe this is just a different way of organizing functions. That is totally wrong. This is a story about functions. The essential point is that this is continuous. You can evaluate functions at a point. You cannot evaluate a vector in L2 space at a point. It doesn't make any sense. And the reason should be clear from today's tutorial, right? If I give you, say you start with a continuous function, which is a vector in there, I can take that continuous function and I can just take its value there and change it. That's some new f prime, which is integrable, and it's a vector in L2, and it's the same vector, right? That's a consequence of today's tutorial. The upshot of that is that there is no way to take an equivalence class in L2 and for the elements of that equivalence class to have a coherent opinion about the value of that equivalence class at a point. That is not a question you can ask about vectors in L2. And that isn't just a technical problem. That is a massive chasm between these two columns. And what that chasm is telling you is that this is not really this notion, this kind of space, is not talking about functions. Precisely what it's talking about depends on who you ask, but I think it's appropriate to say that it's really a space of signals. So this is, one of the contexts in which this Hilbert space is discussed extensively is harmonic analysis. Which, if you like, is the study of signals. So a signal, what's a signal? Well, a signal is a superposition of waves, right? So by the end of the lecture, the content of this statement should be a little clearer, but given that I've discussed that there's a linearly independent dense set in this space given by functions of this form when x equals to S1, maybe it's already fairly clear, and if you're familiar with Fourier analysis, well then you already know in a sense why this is a space of signals. And indeed the modern foundations of harmonic analysis were laid down by people including Norbert Wiener, who explicitly described this space in precisely the way I just did. Okay. So I claim this is not a space which is talking about functions, but it's rather talking about signals. That is, signals propagating on X. Okay, so let's be a bit more technical about that. So as I said, we proved last lecture that these exponential functions are linearly independent in L2, and moreover that they span a subspace which is dense. So that was just a consequence of Stone-Weierstrass via this, and this works more generally for any X compact embedded in Rn once you replace e to the in theta with the appropriate monomials. Okay, so let me give you the upshot of the calculation that we're going to do. So let's take this normalization of those functions. That's still a linearly independent set. Okay, so maybe I'll make a definition. So in a Hilbert space, H, an indexed set of vectors ui is called orthogonal if the pairing is 0 for any distinct pair of indices, and orthonormal so delta ij is the Kronecker delta, so that's 1 if I equals j and 0 otherwise. So an orthonormal family, so by family I just mean index set of vectors. So an orthonormal family is in particular orthogonal, but also has the property that the length of each ui is 1. Okay, so claim. So I'll just list out the claims we're going to prove first. Well, it's that those are orthogonal. And secondly, is that given any f in L2, f is equal to this sum. Well, what do I mean by that more precisely? So that will mean the limit, so it's a series, it's an infinite series, it's the limit as n goes to infinity of these partial sums. And so that's for any f, but if f happens to be continuous, more precisely the class of a continuous function, then that coefficient is just the integral over S1 of f un bar, which is the integral from 0 to 2 pi f theta. All right, so that's the Fourier coefficient. Of f. So that's some complex number, and that's the coefficient that appears in the UN. Okay, so that's the sense in which the appropriate way to think about vectors in L2 is as superpositions of these waves, that is, functions of a fixed frequency varying around the circle. And the coefficients are these complex numbers evaluated by these integrals. Okay. So let's go about proving these statements now. So this is the same statement. And well, it's just a calculation. If m equals n, I'm just integrating this times the conjugate of that. The exponents add up to 0, so it's 2 pi. And if m is different to n, I'm evaluating that. Okay, which is that. But this thing is 0 at both 0 and 2 pi. So that's 0. Okay, so that family is orthonormal. We already know it spans a dense subspace of, well, what I proved last time was that it spans a dense subspace of CTS S1C. Well, I proved this, but the fact that it's linearly independent, I guess I proved in CTS S1C, but that's a subspace of this, so it's true there also. If you like, linear independence can also be derived directly from this calculation. Okay, so this is the statement that is not obvious and requires some effort. So the first step will be the following lemma. So by the way, I'm restricting to the case of countable orthonormal families because it's technically a bit simpler. It's not much more complicated to do the general case, and you need the general case. I mean, it's not that the only interesting examples are going to be countable orthonormal families. I mean, this is countable, this collection, right? It's indexed by Z. Now I'm restricting to the countable case because I need to fit it in one lecture, but there's a small modification and it works more generally. Okay, so let's take a countable orthonormal, orthogonal family. So in H is a Hilbert space. So the series converges if and only if the series of norms squared converges, right? So that's a series in R. Well, what do I mean by this? I mean, that's so to say to say a series, at least indexed by a countable set with a given enumeration in a norm space converges, is just to say that the limit as n goes to infinity of the partial sums exists. That's what I mean. And well, what does this mean? Well, that's a sequence. So you know what it means for a sequence in a normed space or any metric space to converge. So this is within the scope of the definitions you know. And that's what I mean when I say this series converges. Okay, so second statement, if the sum of that series of real numbers is equal to lambda squared, then, well, given what I just said, this exists as a vector in H, and its norm is lambda. Well, I phrased it differently in the notes. No difference really. And the sum is independent of the ordering. That's also important. So more precisely, what does that mean? So this series, how did I define it? I define it as a limit of partial sums. I started with just a collection of vectors, if you like, but to talk about this sequence, I needed to choose an enumeration, right? What I'm saying is that as long as you have this condition, then it doesn't matter what enumeration you choose, all those series converge, and they all converge to the same thing. That's just unconditional convergence, you probably remember, right? Okay, so that's this final statement here. Okay, so let's see how we prove that. The essential point here is just the analogous statement in R for absolute convergence and unconditional convergence of series. All right, so let Sn be the partial sum, and lim little Sn, well, it's going to be a problem, I guess, is the partial sum of the squares of the norms. All right, well then Sm minus Sn squared is the sum from n plus 1 to m ui squared. Now suppose that thing inside the brackets was a sum of two vectors, right? ui plus 1. Well, ui and ui plus 1 are orthogonal. That's the hypothesis. And we know from the Pythagorean law in a Hilbert space, in a product space, that this would just be the sum of the norms squared, right? But just by induction, you can prove that if you have any finite family of things, all of which are pairwise orthogonal, then the same thing works. That is, that you get the sum. Okay, so that's just the Pythagorean law extended by induction. But that's the difference of these things. Okay. So what does that mean? Well, it means that this sequence that's a sequence of vectors in H. To say it's Cauchy in H is to say we can make this small by making m and n simultaneously very large. But we can do that if and only if, I mean, the square doesn't make any difference to whether we can make things large or not, I mean small or not. So that's if and only if this series is Cauchy. So this is capital S. Is Cauchy in R. All right. Okay. So that proves the first claim already. Right? The first claim was that series converges. Now I'm fixing an ordering on the set, right, of orthonormal vectors for the moment. Okay, so to prove that series converges, well, H is complete, right? So to prove that sequence of partial sums converges, that is the SNs, is exactly the same as to prove it's Cauchy. And I just showed you that it's Cauchy if and only if this is Cauchy, and which is to say, since R is also complete, that this converges, which is precisely the first statement that's made there. Yep. Okay, so that finishes off the first claim. Now, suppose that that sum actually suppose that converged to lambda. So that's finite by hypothesis. Well, there's this relationship. Why is that? Well, that's the same Pythagorean idea again, right? If I take the norm squared of this thing, and they're all orthogonal, it must just be the sum of the norms squared, but that's little s. Okay, so that's again the Pythagorean law. Okay. So the norm of this convergent series, well, that's by definition the limit as n goes to infinity of Sn, and the norm is continuous. Which is the limit of the lowercase Sns, and well, by hypothesis, that's lambda. All right, so that proves the second claim. And then there's just the business about reordering. Right, so suppose F is a permutation, that is, it's a bijection. Well, that sum of squared norms of the UIs, those are all positive numbers. So the fact that it converges means that it converges unconditionally. So so that means that this sum converges, where I just change the ordering with the j. Right, that's just using series properties of series in R. But then we can read the first statement in the converse direction, which says that, well, with that ordering, that sum, that series rather, being finite means that the series summed up the permuted way in H of the U's converges. Now, I still have to argue that this sum actually is the same as the sum before. Yeah, so this gets a bit more complicated. Okay, so let's call this thing U. And what we know is that, so that's the definition of what U is, and the second part of the theorem tells us that the norm of U is also lambda, or rather the square. Okay, so now we've got to try and compare, and we want to show that U is equal to that original sum, right? That's the content of the statement. So we'll just compare UN with SM. Okay, so UN is the partial sum of the permuted series, SM is the partial sum of the original series. So that's this. N UFJ N UI. Oh, I did it the other way around in the notes. That's a bit annoying. Okay. All right, so here you've got to be a little careful. So, well, those are finite sums, and the pairing is additive, so I can take both of those sums out the front. That's okay. And then I've got the pairing of U's with other U's, so I know that's either 1 or 0, right? And if it's, well, that's not quite true. I only assumed it was orthogonal, not orthonormal. Okay, so it's the length of Uj, or it's 0, right? Depending on whether Fi is equal to, so that's this. Okay, so now that's U, that's the limit of the UNs, and the pairing is continuous, right? So that is the limit as n goes to infinity of the pairing that I just computed. All right, but what does that look like? Okay, so it's the M, right? Okay, so we're keeping the M fixed. So you've got a RAID in front of you, U0 through UM. And then you're pairing against those things that range from 0 to n, and n is getting very large. Well, for sufficiently large n, you hit all the things between 0 and m, right? No matter what the permutation is. right? So U0 might appear as, the 10 millionth thing in the permuted order, but it does appear, right? So as you take the limit sufficiently large, you're going to hit everything. That's the idea here. So when you compute this, you get the limit, of that sum, and then by the argument I just sort of sketched, you hit everything which is being described by the SM, that is all the things of degree, of index less than or equal to m. Okay, so once you wrap your head around that, that's not too complicated. Well, but then what we can do is, that's an equality of two real or complex numbers, and we can take the limit as m goes to infinity. Now, the pairing is continuous in both variables, so the left-hand side must be the original sum, and the right-hand side has to be the sum over all j of the uj squareds, which is lambda. Okay, so now we're done, because we just compute that the distance between u and that series, we want to be 0. When you evaluate it, right, so this is the evaluation we've done before, so you get this paired with itself, which is that's what, when you expand that as a pairing of that thing against itself, that's what you get. But we know we calculated that to be lambda. We calculated this just now to be lambda, and that's also lambda. Okay, so that's 0, and that proves that that permuted series is the same limit as the original one. Okay, so that's the proof of the claim. Okay, so this is honestly summing up all the things in whatever order you like. Lemma. So we discussed last time the notion of the closest vector to a given vector within a subspace or a closed convex non-empty subset. So let's take an orthogonal family. Could be in an inner product space, but let's say in our Hilbert space. And so you're imagining these UNs, and we let U be the span of the set. Okay, so this is clearly of relevance to the earlier formula for the function f, right? So we start with an orthogonal family, we take its span. That's not everything, but in our case, for instance, it's at least dense. So we take any vector in H, then there's some closest vector in the span to that vector, and I claim it's this, the limit of this series. Now, that series has a limit by what we've just said, so that is a legitimate object, as we'll see, and it is the thing that achieves the infimum of the distance to H. All right, So it suffices. So we characterized the closest vector in terms of orthogonals earlier, right? So it actually suffices to show that that exists. Oh, yeah. I guess I'm skipping a step here. So, all right. So I could go straight to proving it for the infinite case, but then I have to discuss why this converges, which involves estimating that sum of the squares of the norms of these things. That's Bessel's inequality, which I'll do in a second. So for the moment, let's just stick to the finite case. Okay, so that's just an ordinary sum, no problem. This is just spanned by a finite set. Okay, so to prove this is the closest thing, it suffices to pair it with everything in U and show it's 0, but everything in U is a linear combination of the UJs, so it suffices to pair with each UJ to show it's 0. So I just need to show this is 0, but if I calculate that, well, so that's H UJ minus, so by linearity those terms come out the front, so that's the sum over I 0 to n, H UI, UI UJ. And, well, those are 0 unless I is equal to j. I said orthogonal, but it seems like I want orthonormal. Yeah, so let's say orthonormal. Okay, so that's delta ij. So the only sum n that matters is j. Okay, so that's using the earlier lemma that completes the argument. All right, so that's the setup I need. And I need one more thing, which is Bessel's inequality. So this is where something happens. Okay, so this could be infinite. So this is in our Hilbert space H. Okay, so then for H in H, the sum over I and I of H paired with UI okay, you can see why this is significant, right? Because, well, when I was sitting here earlier, I mean, you might want this to exist, even if this is an infinite sum. Okay, well, what would you need for that to exist? Well, I erased it. So if you look at the earlier result, what we'd need for that to exist is we'd need to know that the norm of this squared as a series converged. Well, the norm of that is 1, so that's just really the absolute value of that squared. So if I know the absolute value of that squared, summed over all I is finite, then this expression will make sense. And this tells me exactly that, right? Because it tells me, well, the norm of H is finite, so it tells me that that sum converges. All right, so why is that true? Okay. Well, the way I've written it, I've chosen an ordering already, that's fine. We'll see as a consequence of the earlier result, it's independent of that. Okay, so let's write H sub n for the finite sum. So then by the lemma we just proved, H minus Hn is orthogonal to the first n plus 1 vectors. Okay, so what that tells us is that the norm of h squared, which is the norm of h minus hn plus hn squared, lost the plot here. Ah, yeah, okay. So I just need an inequality, right? So that's okay. And now this by Pythagoras is, well, this is by definition that. They're all orthogonal, so summing it up, no, that's not right. Something's, no. That's fishy. No, I need this step first. Oh, yes, okay, that's fine. It's not much of an argument. Write the same equality twice, it's twice as convincing. Okay, so, well, this is the only step that I need to explain, right? And for that, I just need this to be orthogonal to that. But this is in the span of the ui's. That is, it's in for I from 0 to n. So that's in the span of ui I equal to 0 to n. And we just argued that this expression is orthogonal to that subspace. That was the content of the lemma. So those two things are orthogonal. Therefore, by Pythagoras, it splits like this. That's non-negative, so that's greater than or equal to this. And this, by Pythagoras, again, well, this norm squared by Pythagoras is just the sum of the norm squared of all those things. And the scalar comes out the front with an absolute value, and the norm of that is 1. So that's just this. So that, well, that proves it for n. But what does that show? It shows you that you've got, these are all positive, okay? So you've got a sequence, you're summing up a sequence of non-negative terms which are bounded above. Such a series converges. Right? That's the first thing you learn when you learn about series. So that tells you that series converges, and moreover it converges to a value which is less than or equal to that. So that's just elementary real analysis. So that's true. Okay. So I already sketched how that gets us an infinite series expansion of any vector in our Hilbert space. Okay, so okay, so now consider the situation that we were presented with our example, which is H L2 S1 C and UN equal to 1 over root 2 pi e to the I n theta. Well, I mean, here I'm indexing by non-negative numbers and there by z, but that's the whole reason I talked about the thing not depending on an ordering, right? Because all I care about is that the index set is countable, and then expand it however you like. 0, 1, 3, 5, negative 4, doesn't matter, right? So just choose an ordering of z. That'll choose an ordering of your basis, and then we do the series with respect to that ordering, and the sum doesn't care which order you sum it in, so it's all the same. All right, so this is an orthonormal family. And moreover, it has the property that the span, so let's let U be the span. So we proved that that's dense. Okay, so let's consider that situation generically. So an orthonormal family with U, which is the span over F of the family, are dense in H. Okay, so claim, given F in H, we have that the series converges to F. Okay. So this is the theorem in the notes. There's other parts of it, but I don't have time to cover those, so we'll just do this part. Okay, so let's let F prime be the right-hand side. So I have to convince you first that that makes sense, that is, that that series converges. Well, to convince you that that series converges, by the earlier lemma, I just have to convince you that that series of real numbers converges. But that's, by Bessel's inequality, less than or equal to the norm of F squared. Okay, and that means, by the earlier lemma, that the right-hand side, that is F prime, is defined. And moreover, it's independent of the ordering, as I suggested. Okay, so this is a well-defined thing. Now I just have to compare it to F. But for that, I just take the pairing of F minus F prime with each uj. Now F prime is a series, that is, it's a limit of partial sums, and the pairing is continuous. So I can take those partial sums and take the limit outside the pairing. So that's just the sum from I equals 0 to n of, well, F ui uj, and then take the sum out the front, and this is a number, so it comes out the front. So this is just the same calculation as what happened earlier, so there's a ui missing there. Okay, but that's the limit as n goes to infinity. So for low n, maybe I don't hit uj, right, with the ui, so maybe they're all 0. But eventually I hit it with some I, and then after that in the sequence, they're all 0. So this limit is really just the sequence. It's the limit of a sequence which is 0 and then some number, and that number forever. And that number is, well, exactly this. So this limit converges to that thing, and therefore the difference is 0. And that proves, since this thing is orthogonal to everything, and these span a dense subset, so if you're orthogonal to a dense subset, the kernel of this is a closed subspace because pairing with this is continuous. Okay, and it contains the uj's, and therefore it's all of F. All right. So that implies that F is equal to F prime. Okay, so then in our particular case, we've achieved that goal finally of writing this guy as a linear combination of its frequency components. Now I just want to finish by commenting on this expansion a little. So what does this tell you about H? I mean, the title of this lecture was Coordinates in Hilbert Space. So I mean, when we're thinking about a space like Rn, we know what coordinate directions mean, right? We know that we sit at a point, say in R2, and the degrees of freedom in a point are the coordinate directions, which consist of variations of those coordinate positions. The analogous kind of notion for a point in Hilbert space is not, as you might have expected, taking a function defined on the circle, taking a point on the circle and varying the value of the function somehow continuously around that point. That would have been a natural expectation for what the fundamental degrees of freedom in a function on the circle were. This tells you no. So naturally what occurs when we look at the L2 space is instead the natural coordinate directions are to vary the frequency, or the coefficients, the complex coefficients of the components of a given frequency. So it's really the frequency degrees of freedom which are telling you what intrinsically is the information which determines a vector in the Hilbert space L2. Now, as I said at the beginning of the lecture, everything I've just said generalizes to some degree to the case of X embedded in Rn and compact. So I've outlined in some exercises, if you start with, say, the sphere, you should discover spherical harmonics. If you start with the torus, you'll find pairs of sort of doubly trigonometric polynomials. And so there's a complete story for any of those spaces. Okay, so that's sort of a complete calculation of the L2 space of the circle. And so we'll stop there.